So hello everyone, today's topic is ZK STARKS. In the last lecture we saw SNARKs. Similarly, STARKs are also a proving system used to prove some information without revealing its details. So first let's see the difference between the STARKs and SNARKs. So talking about the transparency, SNARKs are not transparent as we have to rely on a trusted setup. How? Like in the last lecture we have seen that there's a third party that generates a secret key tau, and from that tau that encrypted uh, polynomials are calculated. But in the case of but in the case of snarks there is but in the case of starks there is no trusted party. um, so talking about the scalability, the starks has a logarithmic verifying time, and snarks has also a logarithmic verifying time, but the difference lies in the proving time complexity. The proving time of Starks is linear in polynomial size, but that of Snarks has no limit because of the extensive cryptography used. So, proof size. The proof size of Starks is larger than the Snarks, and the reason we will see later in the lecture. So, the post quantum secure. We have seen Snark use elliptic curve cryptography, and by an algorithm named Shor's algorithm, elliptic curve cryptography can be broken. So what do I mean by broken? So in the last lecture, we have seen that discrete logarithmic theorem in the elliptic curve, which tells that if we know a point alpha g in the elliptic curve, then we can't infer what was the original value of alpha from that elliptic point. So, but in the case of ZK Stark, some collision resistant hash functions are used, which make it quantum secure. So Starks are scalable, transparent, and they provide argument of knowledge. So how they're implemented, these are mainly the 4 steps in the Starks implementation. We will go through each of them one by one. So first is arithmetization. The information that the prover wants to prove to the verifier has to be represented in some form of algebraic form. So the algebraic representation has 2 main components. First is execution trace, and the second is some set of polynomial constraint. So let's understand it with an example. So uh, here's a sequence printed on the screen. It's called collat's sequence, and its properties are that, like, we can start with any positive integer n, and if n is even, like if the current number is even, then the next number would be half of it, and like this is 52, it is even, then the next number is half of it, which is 26. And if the current number is odd, then the next number would be equal to 3 into current number plus 1. Like, 52 gives 26, 26 is again even, and it gives 13, and 13 is now odd. So 13 gives you 13 into 3 plus 1 equal to 14. Like you can see here, 5 is also odd, so we get a 5 into 3 plus 1, 16 here. So this is a collage sequence. So what does the collage conjecture say? It says that if you start with any positive integer n, if you apply the operations mentioned here, then you will always end up with 1. This means that uh, there would always exist a index I, where the value would be equal to 1, and that is where our series would stop. So let's see how I can represent it in the algebraic form. So first is execution trace. So these are the let's define what is execution table first. So execution trace is some kind of table, like, which represent every step of my computation. So like, in this example, what is my computation? I have calculated all the values of this series till I reach 1. So this is my computation that I go from 50 to from every number to every number, and while applying these operations. So in the execution trace, I will represent all of these numbers, and in this example, I have represented them in the bitwise form, where the most significant bit is in the right and the least significant bit is in the left. And The next is polynomial constraint. So like uh, our problem has this constraint that if a number is even, then its next number is equal to n by 2, and similarly there is a constraint for odd number also. So that would be our we will formally define polynomial constraint for that. So these are the four polynomial constraint that we generate for this problem. So like this first term, this first polynomial, first constraint is like simply it's telling that the first term is 52. So like you can see that this is a0 comma j. So a0 represent the first row of my execution trace, and j is my column number. Okay, so like it's nothing but the expansion of this bitwise representation in the decimal form. Okay, so it's telling that when I expand it to a decimal form and subtract the first term from it, then I would get 0. So it's equivalent to saying that my first term is 52. And similarly, as the Collard's conjecture say, the last we stop when we reach 1. So the last term would have to be 1. Like you can see here, the last term is 1, and its bitwise representation is written here from least significant bit to most significant bit. And here is the constraint for that, the last row is 1. And since all of the values are in this table are either 0 or 1, so we also have a constraint for that, like ai comma j square minus ai comma j equal to 0. If you calculate the root of this polynomial, then ai j would be either 0 or 1. So this means that all the values in the execution trace are bits. Now let's come to the final constraint, and this is the heart of our Collard's conjecture. So this was our golden rule of the while generating a Collard sequence, and this is what like written in the fourth constraint. So if we say that like ai comma 0, ai for this is for all rows, okay, and 0 here represent the first column. So this is actually checking if the number is even or odd. If the number is even, then the least significant bit of the number, that number would be equal to 0, and if the number is odd, then the least significant bit of that number would be 1. So if the number is even, then this term would be 0 and this term would 1. So only this term will play into will come into the picture. And if the number is odd, then this term would be 1 and this would be 0, and only this term would be equal to this term only would come into the picture. So uh, let's say this is my uh, ith row, and this is my I plus 1 row. Okay, so uh, the number on the ith row is even. So this rule will be applied on it. So like from this rule, if n is even, then n goes to n by 2. ai plus 1 is equal to ai by 2. And you can see that that is what written in this square bracket, that ai plus 1 uh, is equal to ai by 2. If you calculate the root of this polynomial, then ai plus 1 would be equal to ai by 2. It does not make sense. And so what's the rule for odd number? That 3ai plus 1 is equal to ai plus 1. So this is how I represent my like the constraint on our problem into the polynomial constraint formation. So let's see another example. This time it is Fibonacci number. The information that the prover wants to prove to the verifier is that he has calculated the Fibonacci number till 511, and he knows the value of the 512th Fibonacci number. Okay, so this is equivalent to proving that he has calculated all the Fibonacci numbers till the 512. Okay, so what would be the execution trace of this problem? the execution trace of this problem would be all the Fibonacci numbers till 512. Okay, so first Fibonacci is 1, and this is a Fibonacci sequence is written, and this is a polynomial constraint on the for this problem, that a0 minus 1 0 and a1 minus 1 0, and for this is the Fibonacci recurrence relation, that for all I in the range of this execution trace, the Fibonacci recurrence relation should hold, and that is fi plus 2 equal to fi plus 1 plus fi, and this is the final thing I want to prove. Okay, so we have successfully represented the information in algebraic form. Now in the next step we will do some polynomial conversion. So what's the aim now? So my aim is to transform the polynomial constraint that I generated from the given problem to a single polynomial that is guaranteed to be low degree if and only if the execution trace is valid. A very heavy statement, but it would be clear as we progress through the lecture. So as we have seen in SNARKS lecture, all the things we are doing is not on the range of all real numbers, but some finite field. So that is true in STARKS also. So prover will select a field on which all the mathematical things are happening. Let's say the field he selected as generator element G. So we now think of elements in the execution trace as evaluations of some polynomial fx. What does it mean? That like we have this execution table trace here, okay, and like we thought of every value in this execution trace as to be some output of a polynomial fx, where the xi's are the powers of the generator element. This table would make it clear that we are choosing our x to be the powers of the generator element, and the corresponding output of the polynomial f would be the execution trace element entries, and this is the way we construct a polynomial. So in the generalized manner, it means that for all I belongs to 0 from phi 1 1, f of gi equal to a of I. Okay, so like now you will notice that all my ai's become output of fx. So I can just replace ai by fx here. So you can see these ais are replaced by f here because they represent the same thing. So finally we have a polynomial fx and some constraints that the polynomial should satisfy. Now let's define some set of functions px, qx, rx and sx. Their value is written here, their expression is written here. Now like, if the prover has truly evaluated the Fibonacci number till 511, then all the constraint should like should be true for the execution trace. Okay, so like this fx we built on the execution trace, and this fx was satisfying this set of polynomial constraints. So if we put x equal to 1 in this constraint, we get this constraint that f of 1 equal to 1. And if you can see that if you put substitute x equal to 1 here, then the denominator become a divisor of the numerator. So this means that like if the prover has not truly evaluated the polynomial execution trace, so then the denominator would not be exactly dividing the numerator. Like for example, that could be of the form x minus 5 by x minus 4. Like you can't reduce it to a single polynomial expression. But if the prover has truly evaluated it, then it would become a simple polynomial expression, and that is true for all px, qx, rx and sx. So now what is my equivalent statement to prove? That the four rational function px, qx, rx and xx are not some form of like polynomial written in numerator and then denominator, and we can't just reduce it to the single polynomial, but they are actually a polynomials expression. Next we do is we take a linear combination of all these four polynomials and generate a single polynomial known as composition polynomials. We took some random numbers alpha 0, alpha 1, alpha 2 and alpha 3 and generate a single composition polynomial through it. Okay, so let's analyze one thing. If all these terms are polynomials, then this composition polynomial would also be a polynomial. That is true. Let's say one of them is not a polynomial and like it's of the form x minus 5 by x minus 4. If you can't reduce it to a single polynomial expression, then there's a like there's a very high probability, like close to one, like approaching to one, that the composition polynomial is also like a function of some polynomial written in numerator and denominator. It's not reducible because like you can drag on it on the paper and you will be convinced. Like I have done it and yes, I am like very much convinced. If you can, if you want, you can also do that. So my equivalent statement comes now, instead of proving these all four polynomial these all four functions to be polynomials, all I have to do is just prove that this is a polynomial, not a function, not a like function of numerator by denominator. So proving composition polynomial is a polynomial is equivalent to low degree test of composition polynomial. So uh, like the number of elements in the execution trace was equal to 512 because we have calculated Fibonacci numbers till 512. So when we calculate the fx polynomial through Lagrange interpolation that we discussed in the previous lecture also, the degree of the fx will be at most 511, and we would use this fact to found the upper bound of the degree of these four polynomials. Okay, so like the degree of fx is at most 511 and the degree of denominator is 1, so the degree of px would be at most 510, and similarly the degree of qx would be at most 510 and the degree of rx would be at most 511 minus 510 equal to 1. So degree of rx would be at most 1. So like, so if we can somehow prove that these four polynomials have a upper bound on the degree, then our work is done. So that is what low degree testing is for. It's a method of deciding whether a given function is a polynomial of some bounded degree. So all I have to do is now that our the composition polynomial is a polynomial with a bounded degree. Okay, so we do low degree testing for this, and I will explain two tests for the purpose of low degree testing. First is direct test. So any polynomial of degree less than d is fully determined by its value at any d distinct location. So like this is in consistent with the Lagrange interpolation. Like if you know d distinct unique points on the like number system, like you can uniquely determine a polynomial of at most degree d minus 1 passing through it. Okay, so what the verifier will do, the verifier will ask the prover values of the polynomial at some d distinct points. So he will generate some these d distinct points x1 to xd and a random x0 point, and he will generate provide this d plus 1 points to the prover. Okay, then the prover will provides the value of uh, f cp of x1, cp of x2 and cp of x0 to the verifier. So like as I told that the degree of cp is bounded by the this fx. So the verifier can itself calculate the uh, can interpolate a polynomial gx from the output of the d points that the prover has provided him. Okay, So like these d points will give allow him to compute a polynomial, and then he will calculate the value of gx naught, and then he will uh, compare it with the value provided to him by the verifier. And if that is true, that means that the prover has actually done the computation, and so the uh, proof is done. Okay, but there is a problem in it. Like you can see that the verifying time in it is linear in polynomial size, but as we have seen that the in Starks the verifying time is logarithmic. So we have to improve it. So that's where a technique named FRI comes. Like let's assume this is a polynomial on which we have to prove the upper bound of the degree. So we can represent this polynomial into like in the form of its even part and odd part. So like f of x equal to f of even x square plus x into f of odd x square. So where f of even f of even represents those x values in which the degree is even. So like f of even x equal to 19 plus 34 plus 43 plus 10. Like sorry, it's 10 here and it is 0 here. And similarly f of odd equal to 56 plus 48 plus 37 plus 0 here. This is x cube and this is x, and we are calculating it on x square. So for an extra x term we have added it in like in the outside. Okay, so uh, what prover will do, the prover will represent the polynomial in this form, and then the verifier will choose a random number. For example, in this case he chooses r1 random number equal to 12, and then uh, he will give this random number to the prover, and the prover will now generate a new polynomial from the even part and odd part of the original polynomial. So like this is the expression of the new polynomial the prover generate: f of 1x equal to f of even x plus r1 into f of odd x. So as you can see, the degree of this polynomial is 3, but the degree of this polynomial was 6. So we were able to reduce the degree of polynomial by half. And that's the core intuition of the FRA technique. Like in we will do this step of representing the polynomial into its even part and odd part repeatedly until we get a constant polynomial. So like we started with degree 6 and then we got a polynomial with degree 3. We will again do the FRI on this polynomial, and we will get a polynomial of degree 1 from here. And if we again do it, then we will get a constant polynomial, which means the polynomial of degree 0. So you can see that in like in log d steps you are able to reach the constant polynomial. So that's where the log d factor come. And in further I will discuss how the verifier can then verify the proof. So all the polynomials generated, log d polynomials generated in this step, the prover will store it. Okay, so the process is diagrammatically depicted here. The verify generates a random number alpha 1, it's equal to r1, and then the prover generates some set of f1 here, and the verifier again gives some random number alpha 2, and the prover again generates some f2 here, unless the prover is able to generate a constant polynomial. So all the work done till now in FRI is done by the prover, except for the seed provided to the prover by the verifier. So now verifier needs to be convinced that the prover actually calculated all the polynomials. So how the verification is done? Let's see. So this was the polynomial that the prover had to prove the bound on. So this we saw that we can represent it in the form of f of even plus x into f of odd. And now if you substitute x equal to minus x here, then you will get this equation. And if you rearrange these equations, then you will get the expression of f of even and f of odd in the form of their original polynomial. So like you will, when you will add these polynomials, add these two equations, then this term will be get cancelled, and you can get the expression of f of even. And similarly, when you will subtract f of minus x from f of x, then this term would be get cancelled, and you will get expression of for f of odd. So the prover has generated expression of f of even and f of odd in their in the form of their original polynomial. So now let's take this equation into mind, and like we have representing uh, let's suppose that all the polynomials generated in the FRA step in a hierarchy, like he has f of 0x in the initial, and then from this he generated f of 1, and from this he will generate f2, f3, f4, f4 till he reach a constant polynomial. So let's assume they are in a hierarchy. So you can see that in the hierarchy, the I plus 1 polynomial is determined by the ith polynomial, the even and odd part of the ith polynomial. So if we can somehow represent the even and odd part of the polynomial in the original polynomial, that means I have represented the f of I plus 1 polynomial in terms of the previous polynomial. And that is what we have done in this slide. Like we have represented f of even and f of odd in original polynomial. So if we just substitute these values into this equation, you will get final this equation. Okay, so uh, in the generalizing it, it means that if you know if at the if for the ith polynomial you know the value of f of x and f of minus x on it, then you know the value of f of I plus 1 at x square. So we will use this to verifier will use this to verify the transitions that the prover made in the FRI steps. So uh, here is my CP, the composition polynomial, the original polynomial. It's denoted by CP here, but the CP here is same as the uh, F0 here. So what will the verifier do? Verifier will generate a random number x, and then he will provide it to the prover. The prover will calculate three things, that is CP0x, f which is also F0x, CP0 minus x, and CP1 x square, and prover will provide these three values to the verifier. So what the verifier will do, from these two values CP0x and CP0 minus x, verifier will compute CP1 x square, and from the computed value he would compare his computed value with the value the prover provided to him. So if they are equal, so this if they are equal, that means that the prover has actually like not cheated in the transition from the uh, composition polynomial to the CP1 polynomial. And this step is done in all the FRA stages. Okay, so that's where the that's why the time complexity for verifying the proof is log d. Like there are order of log d polynomials there, and in every polynomials you can see that there are in every step there is some only a constant time in proving the transition from the higher step of to the lower step of hierarchy. So this is how the verifier will verify the uh, FRI polynomials. And uh, how the prover will prove the transition of the trace polynomial to the CP polynomial. Let's see what is a trace polynomial here. Trace polynomial is nothing but the fx polynomial which we generated original from the execution trace. Okay, like this was the polynomial we generated from the execution trace. So trace is like another name of the like original problem. original polynomial. So now what the verifier will do, verifier will again generate a random number x and provide it to the prover, and prover will calculate four things: f of x, f of gx, and f of g square x, and cp0x, and will give the all the four values to the prover verifier. And now what the verifier will do, verifier will compute its own cp0x by using these three values: fx, f of gx, and f of g square x. And how he would do that, he would just put these three values into this set of equations, and from this he would get px, qx, rx, and x sx. And by he knows the values of alpha 0, alpha 1, alpha 2, and alpha 3 because they are publicly available. So he would get the value of composition polynomial at the value x. So he would compare this computed value with the value provided to him by the prover, and if they are equal, that means that yes, the prover has actually made the transition from a trace to the CP polynomial. So this slide represents the summary of the whole lecture. This is the computation that the prover wants to prove that he has done, and he would represent it in the form of some algebraic forms. He would generate execution trace from it, and it has some constraints. And from the execution trace by the Lagrange interpolation, he would get a trace polynomial, and from the constraint, he would get some set of uh, quotient polynomials, and from the quotient polynomials we get a composition polynomials, and on the composition polynomials we apply FRI, and then the verifier ask queries to the FRI. And this was all about the lecture. Thank you.